Hi everyone, I'm Ge from University of Southern California. Today, I will present our work, Contributions of Shape, Text, and Color in View Recognition, which was accepted by ECCV 2022. We are interested in the human vision system, which is a gold standard for many CV algorithms and on challenging tasks. So human vision system provides us a unified image of the world around us, which has multiple features. For example, shape, depth, motion, texture, and color. But which one contributed most during the decision? So we're interested in that question because human's choice or human bias may also represent the most efficient way to solve the vision tasks. Some related works focus on convolutional neural network, which is partial simulation of human vision system. And they find ImageNet pre-trained CNNs are biased towards texture because when they merge the texture and shape image together, the final decision will be based on the texture. And one limitation is this kind of explanation is not self-interpretable. They are post-process check. And we're still curious to the question, what would be the choice of the human vision system instead of CNN? For human, if we ask shape, text, and color, which one contribute most when we distinguish horse and zebra, the answer may be texture. While to distinguish zebra and zebra car, the answer may be shape. So intuitively, the answer is like task dependent. Neuroscientists have some good findings. And they find there are separate neural pathways to process these different features. And shape, color, and texture, they all perform important role in some decisions. So our goal in this paper is to find a general, self-interpretable way to simulate human vision system, and in a pure data-driven learning manner, because both human bias and data-driven learning may represent the most efficient way to solve the task. This is the pipeline of our proposed human vision engine to simulate the human vision system. So A is the human vision system. Given one image, human do some pre-process and different regions of our brain are activated, and finally we do the decision. So similar for our human vision engine, given the image, we do some pre-process, localize the foreground, and for each shape, text, and color, we explicitly extract them and finally combine them to make the final decision. The first part is image parse and foreground identification. Human can localize object intuitively in a complex scene before we recognize what it is. So similarly, we use entity segmentation, which is an open world model which can segment the object from image without labels. For example, each color represents an entity, even though we do not understand what it is, but we can know they are separate entities. And humans have top-down attention, which help them to localize the interest object. So we know, given this image, we want to classify the foreground instead of the background. So similarly, we use GradCam to help localize the region contribute most to the decision, which can help us to identify the foreground. These are some results of foreground identification. Next, we separately design the Shape Extractor, Text Extractor, and Color Extractor to simulate the separate neural pathways in the human brain, focusing on the different property. For Shape Extractor, we want to keep both 2D and 3D shape information while eliminate the information of text and color. This is the result if we only use the 2D information. And this is the result after we add the 3D depth prediction on the 2D shape, we get the 3D representation of the shape, which is a full-field version of shape representation. For the Texture Extractor, we want to keep both local and global texture information. So given an input image, we first turn them into grayscale and then crop them into patches. And we compute the overlap between the patches and the foreground. Only the overlap larger than threshold will put into a pool, and then we randomly select some patches from the pool to form the texture representation. Specifically, we design an adaptive strategy where the patch size and the location are adaptive with the object size to minimize the information loss of texture extraction. For the color extractor, we won't destroy the shape and texture information while preserve the color statistics. We propose two methods. In method 1, we use phase scrambling, where we first transform them from image domain to the frequency domain, and then the signal is randomly scrambled, which will destroy the shape information while preserve the color statistics. Finally, we transform them back to the image space. So you can say the color representation has no shape or texture information, only keep the color statistics. Another method is color histogram, where we predefine some color and use the size of area to represent their histogram of color. Here are more examples. You can see given some original images, we have some segmentation and we select the foreground and we can have their shape, texture, and color representation. After we obtain those separated features, we train 3 feature encoders focused on embedding their corresponding sensitive features, which will also create 3 latent space. For example, in the shape latent space, similar shape will have similar embedding. And during the training, we use class label as supervision. To verify the performance, we create 3 bias datasets from ImageNet. In the shape bias dataset, use shape can easily make classification decision, while texture and color may be hard. Similar for texture and color bias dataset, where use the bias feature is easier to make classification. This is the main result of t-SNE visualization for the 3 encoders, shape, texture, color on 3 bias datasets: shape bias, texture bias, and color bias. And each color represents 1 class. We can see the t-SNE results are separated perfectly on corresponding dataset, which is the diagonal, but not as well on the other dataset, which is off diagonal. This shows the feature encoders are predominantly sensitive to their corresponding features. For example, the shape encoder separate well on the shape bias dataset, but not that good on the texture and color bias dataset. Finally, we need to aggregate those extracted feature representation and conduct the final object recognition. We concatenate the shape, texture, color representation and go through MLP to give the final decision. And this is the classification performance. And we put different input and we have different results. So the FeatureNet consistently obtain the best performance on their own bias dataset, and when we aggregate all, we have better performance. To summarize the contribution, we propose a gradient-based contribution attribution. Basically, we compute the contribution of each features to the final decision. Okay. To obtain the class-specific contribution, we just compute the average of all images belong to this class. Similarly, we can get the task-specific contribution by aggregate all classes in the dataset. This is the contribution of shape, text, and color on different bias dataset. We can say in the shape bias dataset, shape contribute most. Similarly, texture contribute most in the texture bias dataset, and color contribute most in the color bias dataset. So with the gradient-based contribution attribution, so given any environment dataset, we can summarize the most important features for the whole task, which is task-specific contribution. For example, color is the most important feature overall for classification within the COB dataset, which makes sense, right? Where their shape and texture are similar. Also, we can conduct for the class-specific contribution. For example, shape is the most important feature to recognize both in the iLab 20 million dataset. So now let's compare the performance of our proposed human vision engine to human vision system. We design a human experiments. So images will be represented as separate features, and we test the accuracy by asking human to make classification on the single feature. For instance, in the shape bias dataset, we give only the shape information of an object, and we want the human to make classification, okay, which class it belongs to in the following examples. Here are the results of human experiments on the 3 bias dataset. Compared with the Human Vision Engine, we can say Human Vision Engine and humans predominantly use the same specific features to support object recognition for a specific class. For example, if we use only shape information, we have the higher accuracy on shape bias dataset. So similarly, shape contribute most on shape bias dataset for Human Vision Engine. So human use texture have best performance on texture bias dataset. So similarly, on text bias dataset, Human Vision Engine find texture contribute most. Next, we use our Human Vision Engine to explore more humanoid applications. Here is open world zero-shot learning. Open world means we do not need humans to predefine the detailed attributes labels for each classes. The assumption is, given an unseen image from unseen class, humans can still describe it with their learned knowledge. So there are 2 steps. Step 1 is open world image description. We use our featureness to describe the unseen image. So given image, we say from shape perspective, it looks like a horse and donkey, right? From the texture perspective, it looks like tiger and piano case. From the color perspective, it looks like panda and penguin, right? We can retrieve those anchors from the latent space, and those anchors will be used in the next step called reasoning in the concept net. Right? We use those anchors to find, okay, which class has nearest distance to those anchors to make the final decision of reasoning. And here are the results. In the challenging scenario, we perform better than the traditional baselines. Here the second humanoid application, cross-feature imagination. So human can imagine object when seeing only one aspect of the feature, especially when the feature is prototypically. For instance, we can imagine a zebra when we only see is the stripe texture, right? So this task is similar but harder than the classical image generation task. The challenge 1, the input features is dynamic, which can be any feature among shape, text, or color. And challenge 2, there are ambiguity and uncertainty for the target, especially for the input feature is not prototypical. We use 2 steps to solve the problem. In step 1, we train a feature agnostic net to create a multi-feature shared embedding space where different kinds of features have the similar embedding as long as you belong to the same class. And the second step, during generation, given any feature, we can first retrieve the other 2 features in the shared latent space, and then take the 3 features as input to generate the final imagination image. So here are the results. So given the different input features, our method can first retrieve the corresponding other features and then make the final imagination. Okay, this is the original images which can be treated as a ground truth, and the synthesis one is quite, makes sense. The baseline is we use 3 pix-to-pix scan where each scan only responsible one feature, but the performance is not as good as ours, especially for texture and color. To summarize, we explore the task-specific contribution of shape, text, and color feature in human vision recognition. And we propose our Human Vision Engine, which explicitly and separately compute these features from images and then aggregate them to support image classification. And the Human Vision Engine can summarize and rank order the task-specific contribution of the 3 features to object recognition. And we use human experiments to show our Human Vision Engine has a similar feature contribution to humans on specific tasks. We show that Human Vision Engine can help simulate more complex and humanoid applications. Thanks for all of the co-authors, and our code are released on GitHub. Thanks.